Shoot. Okay, so let's do x plus 5 times 3x plus 6. Oh, I didn't mean to do x plus 5 twice in a row, but there it is. So again, we're going to distribute the x. So
That's like foil.
I mean,
When it's 2, is it foil?
you don't, I could go off on this for a very long time, but FOIL is an acronym to help you remember how to do one specific case of multiplying polynomials. And you could just learn how to multiply polynomials, which tells you how to do all of them. It always just seems really silly to me that we have this acronym for like one problem. You know, and then you give somebody a problem that has like a trinomial in it, and they're like, but I can't FOIL. Like, it's all the same thing. Like, FOIL just means distribute each of the terms in the first one to all of the terms in the second. So the process is exactly the same. Some of the acronyms in high school math don't make any sense to me.
Yeah, that was college. That was 65.
Yes, that is true.
Yes, it was high school.
So x times 3x is 3x squared. And then x times 6 is 6x. And then we're going to also distribute the 5. So, whoops, 15x plus 30. And then we can combine like terms. Make sense? Okay, so let's do one with multiple variables. So a plus b times a squared, whoops, I want that to be a minus b, plus ab plus b squared. So when we multiply, well, when we do anything really with multiple variables, the general rule is that within each term we put the variables in alphabetical order. So the reason for that is just so if you have a squared b and you have b times a squared, like you see that they're like terms, right? Just so that everything looks consistent. It's not like more correct or anything like that, but it helps with consistency so we can recognize like terms when we have them. So we're going to start by distributing the a. So a times a squared, a times ab, and a times b squared. So a times a squared, that is 3 factors of a. And then a times ab gives me 2 factors of a and then 1 factor of b. So a squared times b. And then a times b squared, well, that's just 1 factor of a, 2 factors of b. So ab squared. So far, so good? And then next we're going to distribute that negative b. So again, just multiplying it by each of the terms. It's going to make all 3 of those terms negative because inside that trinomial we have positives and we're multiplying each of those by a negative. So minus, if I do b times a squared, then I have 2 factors of a, 1 factor of b. So minus a squared b. And then b times ab is 1 factor of a, 2 factors of b. So minus ab squared. And then b times b squared gives me 3 factors of b. And this works out really nicely because a squared b minus a squared b is 0. And ab squared minus ab squared is also 0. So we get a to the third minus b to the third, which turns out so pretty. What should I do here? So let's do 2x minus 5 squared. How do I square a binomial? Yes.
Just write it again.
Yeah, you multiply it by itself, right? Remember we talked on Monday about the freshman's dream, how we all just want to say it's like the first term squared minus the second term squared. That doesn't work because exponents don't distribute over addition and subtraction, right? So we just have to actually multiply this binomial by itself. Because there is subtraction in the parentheses, when I write this out as repeated multiplication, there are still multiple operations, right? So I still have to do distributing. It doesn't all just end up being multiplication so that I can rearrange things. So 2x times 2x is 4x squared. 2x times negative 5 is negative 10x. Negative 5 times 2x is negative 10x. And negative 5 times negative 5 is positive 25. And so we get 4x squared minus 20x plus 25. So then what do you guys think about Whoa, okay. What?
Okay, never mind.
Okay. Yeah? About this one.
Break it up 2 times again.
Right, so we have to multiply x plus 2 times x plus 2 times x plus 2. Now I will tell you, no matter how you try, there is no way to multiply 3 factors all at the same time. The way that we multiply more than one or more than 2 factors is to multiply 2 of them and then multiply the result of that by the third. So if you think about multiplying numbers, we do it so quickly in our heads that sometimes it feels like we're doing it all at once. But in reality, what we do is 2 times 3 is 6, and 6 times 5 is 30, right? It always goes in 2 steps because you can only multiply in pairs. And so the same is true with polynomials. I can't like distribute that x to like more than one set of parentheses. So what we're going to do is just look at this guy. We're going to multiply those 2 polynomials, and the result of that is going to go in parentheses, which we will then multiply by the third. So x times x is x squared, x times 2 is 2x, 2 times x is 2x, and 2 times 2 is 4. And then my extra factor of x plus 2 just comes along for the ride. And then I can combine like terms. So x squared plus 4x plus 4 times x plus 2. Good? So this whole thing is those first 2 factors. And now we're going to multiply that by the third factor. So we're going to distribute x squared to both terms, 4x to both terms, and then 4 to both terms. So we have x squared times x is x to the third. X squared times 2 is 2x squared. So that's what I get just from distributing this first term. And then we'll distribute that 4x. So 4x times x is 4x squared. 4x times 2 is 8x. And so that's what I get just from distributing this term. And then we'll distribute the 4. So 4 times x is 4x. 4 times 2 is 8. And so then I distributed that term. We're done. One thing that you can use just to kind of check to make sure you didn't forget anything or do anything twice is that the number of terms that you get before you combine like terms should be the number of terms in the first polynomial times the number of terms in the second polynomial. So if I have a trinomial times a binomial, I should get 6 terms, because I have a 3-term polynomial and a 2-term polynomial. And notice that 1, 2, 3, 4, 5, 6. I do get 6 terms. Before you combine like terms, after you combine like terms, you're putting stuff together, which we'll do now. So x to the third plus 6x squared plus 12x plus 8. So anytime you're multiplying 3 factors, the key is to just multiply 2 of them, keep the result in parentheses, and then multiply by the third. Anytime you have parentheses, the way that you know you can drop the parentheses is when you've done all of the operations outside of the parentheses. So here, when I did this multiplication, I couldn't just get rid of the parentheses because I haven't done that multiplication yet. So I can't drop all my parentheses until I've done the operations between them. So one that you'll see pretty often is like 3 times x minus 2 times like 3x minus 5. So where you have a monomial times 2 binomials. Now when you multiply 3 factors, you can do it in any order you want. Like over here when we did 2 times 3 times 5, we could have done like 3 times 5 first. Right, the order that you multiply in doesn't matter because it's commutative and also associative. So my general rule when I multiply 3 factors is to multiply the ones that are most alike first. It cuts down on the distributing. So if I have 2 binomials and a monomial, I'll multiply the binomials first and then distribute the monomial. So this 3 is just going to hang on for the ride. Minus 5x minus 6x plus 10. Always combine like terms, so finish doing one product completely before you start doing another one. So don't jump to distributing yet because you want to combine your negative 5x and negative 6x. So 3 squared minus 11x plus 10. How are we doing? Did I do something not true?
How'd you get the first part again?
5x.
So,
Oh, yeah,
I did x times 3x and then x times negative 5.
Oh, and we're leaving the 3 on the outside?
Right. Because we're just choosing 2 of the factors to multiply first. And then I did negative 2 times 3x and negative 2 times 5. And so then we combine those like terms. Now, notice I didn't drop my parentheses because I haven't addressed the multiplication that is outside of them. And so now I can distribute that 9 or that 3 and I get 9x squared minus 33x plus 30. You could distribute the 3 first, but if you do that, note that it only distributes to the first factor. Like you can multiply 3 times x minus 2 and then multiply that by the third one. I find that people get tempted to like try to distribute the 3 to everything when they do that first. That's why I like to do the other one first. In contrast, you could have 2 monomials. Times a binomial, in which case I would do, again, the 2 that are most alike first. So 4 and 3 are both monomials. 4x squared minus 9 is a binomial. So I would just multiply that 4 and 3 first.
So then that kind of goes against doing parentheses first. Right?
So parentheses isn't an operation. You can't do parentheses. You can do operations that are inside parentheses, which is what we mean when we talk about order of operations. What we're doing when we distribute is the operation of multiplication. And so it doesn't have anything to, the parentheses are just grouping. So in order of operations, when we say to do parentheses, what we mean is to do operations that are inside the parentheses. We can't do any operations inside our parentheses here because we can't combine unlike terms. When we distribute, we're doing the operation of multiplication.
But, so like my gut feeling would be to distribute the 3 into that.
Uh-huh.
Would that be the same thing as harder, or?
You can do that. You just end up having to distribute more.
Gotcha.
So like you could go like this. And then you have to distribute the 4.
Okay. I see.
I'm not sure I enjoy that multiplication,
Yeah.
but you can do it. I find that it's a little bit less work to multiply like the ones that are alike first, so the monomials first, so then you're distributing just once. So then we get 48x squared minus 108. So it's not right or wrong to do it any which way. Like you can multiply any 2 factors and take that result and multiply it by the 3rd factor. I mean, we could have multiplied 4 times 4x squared minus 9 and then multiplied by the 3 if we wanted to. Certain ways might be a little more efficient than others, but none of them are incorrect unless you do it incorrectly.
I probably know the answer to this, but.
That's okay. Ask anyway. What's up?
So, back to the grouping.
Yes.
So if I had like terms in the
Yeah.
grouping,
Uh-huh.
and I'm still multiplying, I could combine those inside the parentheses
Oh,
first.
yeah, like we did right here.
Okay, I was just thinking of it, but I guess that's the same as that there then.
Yeah, so in terms of order of operations, when we have variables involved or polynomials, inside the parentheses, the only operation to do is combining like terms. Once you've combined the like terms, you're on to multiplication, and that's where the distributing comes into play. Other questions? Okay, I've got one for you guys to try. Ready? It's a good one. 3x times 2x plus 1 squared. Times 2x plus 1 times 2x plus 1. And most of you did 2x plus 1 times 2x plus 1 first. We could have done 3x times 2x plus 1 first, as long as you keep your parentheses. So I believe that most of us came up with 4x squared plus 4x plus 1, not 2. Hopefully it makes you feel better that half of you did it. And then distribute that 3x. So we get 12x to the 3rd plus 12x squared plus 3x. Everybody feeling good about that? Okay, so let's do a couple more, just kind of combining all of these. Yesterday we did addition, subtraction. Today we did multiplication. We can, of course, have both addition, subtraction, and multiplication in the same operation, or in the same problem. So for instance, like 6x plus 1 times 3x minus 4 minus 2x plus 1 times 3x minus 8. So in terms of order of operations, we see that we have multiplication here. We have 2 things multiplied minus 2 other things multiplied, right? So we always want to do multiplication first and then the subtraction. So we're going to multiply this guy and this guy first. However, there is still operations outside of those two multiplication problems, right? There's still subtraction that's happening outside of that, and so the result of both of those is going to go in parentheses because we haven't dealt with that subtraction yet. So when I multiply, in parentheses, I have 18x squared minus 24x plus 3x minus 4. And then minus, and again, in parentheses, because we haven't addressed everything outside of the parentheses yet, we have 6x squared minus 16x plus 3x minus 8. And then we'll combine like terms within our parentheses. So always finish simplifying within the parentheses before you do anything else. So 18x squared minus 21x minus 4, and then 6x squared minus 13x minus 8. So now we're ready to do our subtraction. Looking to the left of that first set of parentheses, it's not being multiplied by anything. There's nothing, there's no negative or other number to distribute. And so that first set of parentheses we can just drop. But notice that I wrote it and then I thought about whether or not I needed the parentheses before I just dropped them. So it's not one of those things where we're like, why'd we bother writing them when we don't need them? It's that you want to think about if you need them before you get rid of them. So far, so good? And then that second set of parentheses, we have a negative in front of. So that's like a factor of -1, which we need to distribute to get rid of the parentheses. So that's going to give me a negative 6x squared, a positive 13x, and then a positive 8. At which point we're now ready just to combine like terms. So 18x squared minus 16x squared is 12x squared. And, oh gosh, what is that, 7?
Isn't it
21. No, it is 8, yeah, thank you. And then -4 and positive 8 is a positive 4. So this is really similar to like what we did at the very beginning of the course, right? We just happen to have more powers of x involved. So instead of just like having an x term and a constant term, now we've got maybe an x squared or x to the third. But as far as the process of it, it's just like what we were doing before, as far as like working your way out from the innermost set of parentheses and just being really careful that before you drop any parentheses, you're like thinking about if there are operations to do in order to drop them. We never want to just like get rid of parentheses without thinking about why it's okay to do it. That's where we start making mistakes. Because sometimes we need them, sometimes we don't. And if we just start generalizing, then we end up dropping them when we need them. Okay, one more problem. This one looks really awful when I first write it down, and I promise it's not as bad as it looks. Fair warning. So 2x to the 4th squared plus 5x to the 4th times 3x to the 3rd minus 2x squared times x to the 3rd squared plus 5x times x squared to the 3rd plus, I warned you, plus 5x squared. No, don't quit, because this is not that hard of a problem, and the reason I'm doing it is to show you that, like, a lot of times in math, it's just more how scary it looks that makes it difficult than how difficult it really is. If we can learn to break these things down into smaller pieces that aren't as daunting, then we don't freak out when we see stuff like this. So in reality, what's going on here is notice that I have a bunch of things that are being added and subtracted. If I look between each addition and subtraction problem, I just have like an exponent problem like we did on Monday and yesterday, right? Like 2x to the 4th squared. That's something we did on Monday, yeah? So on its own, that's not so bad. And same with what's in each other term. So if we think about order of operations, we want to do multiplication and exponents first, right? So that means you can even like just kind of draw like a line. Where each addition and subtraction is, and then like address each of those individually without thinking about the other ones, because we don't have to do this all at once. We're going to simplify each term first, and then we'll worry about the fact that we're adding and subtracting them. So if I have 2x to the 4th squared, that is 2 squared times x to the 8th, which gives me 4x to the 8th. Yeah? And then 5x to the 4th times 3x to the 3rd. Well, my coefficients give me 15. And then 7 factors of x. And I'll put back in my addition and subtraction here in a minute once I simplify each one. And then, so now let's look at that 2x squared times x to the 3rd squared. What's up?
So, okay, why isn't the 2x or squared broken out twice, like you did prior?
Well, because there's no addition or subtraction inside the parentheses.
Okay, so that's the rule, that if it has addition and subtraction, then you gotta do it 2 separate times, or whatever.
So, remember when we did this guy? If we write each of those out,
Right.
this becomes all multiplication, which means that we can rearrange the factors. And so this is the same as 5 times x, which is how we get that rule that we can apply the exponent to each one of the factors individually. When we write this out, it is not all one operation. There is multiplication there and there's addition. And so we can't rearrange the x's and the 5's. And so there's no way for us to get like 2 x's together and 2 5's together. And so the only way to do that is to actually distribute. But because when I have multiplication inside the parentheses, what that's really saying is the whole thing is a multiplication problem. There's no other operations going on. And so I can rearrange all of it as much as I want.
That was never explained to me why that.
No, that's a great question. Because it's one of those things where we want to get away from like seeing parentheses and thinking something and look for the actual operations. So look for addition, look for multiplication, look for exponents, because parentheses can mean a ton of different things. They're just a way of grouping operations. What the actual operations are that they're grouping is much more important than the fact that we use parentheses to group them. So here we're gonna do that exponent first. So we'll do x to the 3rd squared first. So I have 2x squared times x to the 6th. And then we can do the multiplication. So my coefficient is 2, and then I have 8 factors of x. And again, I'm just leaving the addition and subtraction alone for now. I'll just carry it down in between the results of each of these. And then, so this 4th one is essentially the same as the one we just did, right? So I'm going to raise x squared to the 3rd power first. And then multiply. So I get 5x to the 7th. And then this last one, we are multiplying 3 different exponential expressions, but notice, again, in the parentheses, there's no addition or subtraction. This is all multiplication. So I can multiply 5 times 2 times negative 2, which is going to be negative 20. And then x squared times x to the 4th. Well, that's 2, 3, 7 factors of x. So x to the 7th. So bringing down my addition and subtraction, that gives me 4x to the 8th plus 15x to the 7th minus 2x to the 8th plus 5x to the 7th plus negative 20x to the 7th. And now we just combine like terms, right? This wasn't so bad. It looks really daunting. It looks really messy. But that's where, again, you want to look at want to look for operations. So look first for addition and subtraction and be like, okay, I can separate everything where they're being added and subtracted and do what is between them first, and then worry about actually adding and subtracting. And that way you can break it down into smaller pieces. So let's see, I have 4x to the 8th minus 2x to the 8th is going to give me 2x to the 8th. And then 15 plus 5 is 20, minus 20 is 0. So my answer is 2x to the 8th. Is that not wicked cool? How it like looks so crazy, and now it's like just this little one term. It's so fun. You guys want to do one like that? I think you probably want to try one, don't you?
Do we have a choice?
I mean, you always have a choice. No, that's enough. Can you read all those exponents? They're kind of messy. This one's a 3. I'll give you a hint, which is that these should all end up being like terms. Oh, wait, no. I just lied to you. Because I meant for this to have another 2. Sorry. So I believe we got 16x to the 6th minus 4x to the 6th plus 27x to the 6th minus 36x to the 6th. True? And then, oh gosh, negative 20 plus 27 is 7 minus 4 is 3x to the 6th. Yeah? No, where?
Oh, never mind. Hold on. How'd you get 2796?
So 3 to the 3rd is 3 times 3, which is 9 times 3, which is 27. Good?
Yeah.
Okay. Any other questions on this one? You guys feel good about multiplying? I'm about to go on to dividing, but we can talk more multiplication if we have questions. Yeah, Amanda, we feel great about it.
Just love it.
Right?
No problem.
Okay. Let's divide. So we're going to kind of do this in stages. We're going to divide a monomial by a monomial, and then we'll divide a polynomial by a monomial, and then we'll do polynomials by polynomials. We end up focusing mostly on polynomials divided by polynomials because they're like the new thing. But don't forget that there's a simpler way if your denominator is a monomial. So like if we do, so this is 4.8. Dividing polynomials. So if we do like negative 42x to the 2nd y to the 5th divided by 3xy to the 2nd. You guys all agree with me that this just looks like what we've been doing all week? Right? Like, I guess it was Wednesday that we did 4.1. It seems so long ago. I think I've been saying Monday all day. But we're just going to divide negative 42 by 3. Then we'll do the quotient rule with x squared and x, and then do the quotient rule with y to the 5th and y squared. There's no addition or subtraction here. And so this is all just multiplication division. So we're just going to do it factor by factor. So negative 14 x y to the 3rd.
Oh, so now we're just gonna actually divide the
Right. Well, we would have.
whatever they're called.
We would have actually divided them before as well if we could, right? So same thing here. If I had like 42 over 12, I would be able to simplify that, but like not get a whole number just because it doesn't go in evenly. So then we're going to extend that idea to dividing. So this is like monomial divided by monomial. Now, when we have a polynomial divided by a monomial, it turns out that if you're just dividing by one term, that division basically distributes just like multiplication. So if I have, can't see, 9x to the 8th plus 12x to the 6th divided by 3x squared. Remember from when we were doing graphing and we solved for y, right? That if we divide both sides by something and there's two terms, that we can just divide each term individually by that divisor. So this is the same as 9x to the 8th divided by 3x squared plus 12x to the 6th divided by 3x squared. And there's a couple reasons that that's true, or a couple ways we could think about it. But if you think about going backwards, remember that if we have common denominators, we keep the common denominator and just add the numerators, right? So we're just splitting that process up. So instead of like saying 9x to the 8th over 3x squared plus 12x to the 6th over 3x squared is the same as just adding the numerators and putting the whole thing over a single denominator, we're just breaking that apart, so that we can then treat each term the way we did that first problem, right? So we have 9 divided by 3 is 3. X to the 8th divided by x squared is x to the 6th. And then 12 divided by 3 is 4. And we get x to the 4th. So notice that in both of these, the thing I am dividing by has a single term. And that's the only time you can use this process, is if your denominator or your divisor is a single term. So let's do one more like that. And division is written a bunch of different ways, so just for some variety, because you'll see it in a bunch of different ways, we'll write it this way this time. You know what, I'm not going to have enough room. I'm not going to try to smush this in here. That would be silly. So 15x to the 4th, y to the 8th. Oh, I said 6th. Minus 3x to the 3rd, y to the 4th. Plus 18x squared y to the 3rd. All of that divided by 9x squared y squared. So this is the same as the fraction with the entire trinomial over the monomial. So 15x to the 4th y to the 6th minus 3x to the 3rd y to the 4th plus 18x squared y to the 3rd all over 9x squared y squared. Those are identical problems. And so when I look at the denominator, I notice there is no addition or subtraction. So that's a monomial, which means that I can just divide each term in the numerator by that monomial. So this is 15x to the 4th, y to the 6th, over 9x squared y squared, minus 3x to the 3rd, y to the 4th, over 9x squared y squared, plus 18x squared y to the 3rd over 9x squared y squared. And so then, again, just like those last problems we were doing, we're just going to look at this term by term. We don't have to do it all at once. So this first one, I have 15 over 9, which simplifies to 5 over 3. Ugly 3. And then x to the 4th over x squared is x squared. And y to the 6th divided by y squared is y to the 4th, yeah? And then 3/9 simplifies to 1/3. And then 1 factor of x, 2 factors of y. And then go ahead and finish that last term. What'd you guys get for the last term?
2y.
Yep, just 2y, good. So the x squareds just cancel. And then y to the third over y squared is y, and 18 divided by 9 is 2. So again, this works when you have a monomial in the denominator. Remember that you can do this when you have a monomial in the denominator so that you don't like try to do long division with it, which gets really tedious and is unnecessary in this case. Now, when we have a polynomial in the denominator that has more than one term, theoretically we could do this. Like if I have 3x to the third plus 8x squared plus 6x plus 4, and I want to divide that whole thing by x plus 2, what's up?
Add them all together.
Well, they're not like terms, so we can't add them up, right?
Yeah.
And so when I look at this and I think about what we just did, it is true that this is equal to 3x to the third over x plus 2 plus 8x squared over x plus 2 plus 6x over x plus 2 plus 4 over x plus 2. This is true. However, I can't do a darn thing with that. Like you can't divide 3x to the third by x plus 2. Let's think in terms of what we talked about yesterday with place value. So, which one do I want to do? Let's do like this one. Or no, this one's a better one. So if I just look at 6x over x plus 2, it may be tempting to like cancel off the 2, right, and get a 3 and like cancel off the x. So theoretically, this whole thing is what, equal to 3? So think about it this way. If this was the number 60 and this was the number 12, could we, sorry, not, yeah, that is, yep. Could we cancel this and put a 3 right there? Like, does that make any sense? I hope not.
What's division? No.
I mean, like you can't cancel just like the tens place with the ones place, right? Like, because that 6 and the 2, they're not factors. So the same would be true if we tried to cancel that 6 and 2 and call it 3, right? Because when we have more than one term, that's just saying we have multiple place values. And so what this is really like is if I were to write this as 60 over 10 plus 2, right? And so saying that I'm going to cancel that x would be like saying, oh, I can cancel that factor of 10 and also this factor of 2 and get like what, like 3 over 1? Like, you guys agree that that looks really silly when we do it with numbers? So the same is true when we're dealing with polynomials. We can't cancel terms, things that are added and subtracted. That's why when we simplify our fractions, like we do factorizations, right? So the entire top is multiplication, the entire denominator is multiplication. Because if you cancel a term, what you're doing is you're like canceling place values. That would be like saying that if you have this fraction, that you could be like, that's equal to 1, right? We can't cancel place values. It just doesn't work that way. Although I went to a conference and I attended a talk, this guy like he wrote a whole computer program to find like fractions that you could do that with, like that just coincidentally, like it worked to cancel. It was like 2 hours of nonsense. It was kind of funny. We won't go there. But you guys see like that doesn't make sense to cancel place values like that. So that's what you're doing if you try to cancel terms of a polynomial. So anything that's being added or subtracted is you're like trying to cancel place values. So instead of doing that, what we have to do is long division. So just like we do with numbers, I'm going to get rid of all of this. So even though it's true that you could divide each term by the denominator, it just doesn't get us anywhere. Like it doesn't actually help us to simplify this expression, which is why we do it differently than the problems that we just did. It's not that like the same rules don't apply, it's just that the rules don't get us anywhere when we have more than one term in the denominator. So before I do this, we're going to do this problem. We are going to divide 3,864 by 12 using long division. I need like some lined paper here because this is, I never get this straight. Let's see. Okay. So we have 3,864 divided by 12. So the first thing we do is we look at 12 and 38. And we say 12 goes into 38 3 times. And then what's our next step?
Put the 36 below 38.
Right, we multiply 3 times 12, right? And then we subtract. And whoops, that's not a 12, it's a 36. And it turns out what you're really doing, because this is in the hundreds place, what you're really doing is multiplying 300 times 12.
Isn't that 4 times 12 is 36?
3.
That's
48, but yes. Because 3 times 1 is 3 and 3 times 2 is 6.
This might not do well on my test.
It's okay, little things like that aren't the important thing. So what we really did was multiply 300 by 12, and then we subtract next, right? And we get 264. Isn't 3,864 minus 3,600 264?
Okay, what are you doing?
Nothing. I'm doing long division. I'm saying that 12 goes into 3,800 3 times, and then I have 264 left over.
But that's not the way you do it.
Yeah, it is.
Not the way I do it.
It's because bringing something down is not a mathematical operation. You're not bringing something down. When you go like this, and you write a 36 right here, and then you like do an arrow, what you just did was 6 minus 0. Right? I mean, like, there was nothing under the 6 to take away from it, and so we just ended up with 6.
26.
Well, I mean, yeah.
It should be 2, 24, which are doing 24.
But let's do math, because arrows aren't math.
Well,
What we did when we draw that arrow is we did 6 minus 0. That's how you get 6. And you can also do 4 minus 0 and get 4. The reason that keeping place values all lined up when you do division is so important is that when we write that number 3, we're really writing the number 300. It's in the hundreds place. Here we're saying that 12 times 300 is 3,600. And so then we subtract it, and we end up with 264, and then we do exactly the same process. So looking at the first 2 digits of each one, 12 goes into 26 2 times. But what we're really doing is saying that 2 is really a 20, right? It's in the tens place. And so we get 240, and subtracting gives us 24. This is long division. This is what you've been doing. People just use stupid words for it that have nothing to do with math. And some really funny symbols.
Bastards.
People like to put X's in weird places. I will never understand some of this stuff. So then 12 goes into 24 twice, which is in fact the number 2 because it's in the ones place. And so then when we multiply, we get 24. We subtract, we get 0.
You're just putting zeros where we didn't never put zeros.
Right, so I can actually do math with them.
It's the same thing, but
Yes.
I'm not doing math when I divide.
Well, you are. You're just, somebody called it something else. You're really just doing subtraction.
I'm doing old school.
Subtraction. So now, let's do this problem. It is exactly the same problem. So I have a 3 in like the thousands place, an 8 in like my hundreds place, a 6 in my tens place, a 4 in my ones place. And in the denominator, I have a 1 in my tens place and a 2 in my ones place, yeah? So if we think of these as place values. So the process for this is identical. We have to use some slightly different words in order for it to make sense. But it's kind of cool because when we do long division with numbers, we're not allowed to overshoot. Because when we subtract, we can't get a negative number. However, because in numbers, we can't have negative digits, right? Like you can't have a negative 2 in the tens place. That just doesn't make sense. But with polynomials, it's okay for our coefficients to be negative. So even if we overshoot, we're still cool. So it turns out that this is actually a little bit less restrictive than when we do it with whole numbers because we don't have to worry about the carrying, the borrowing, the negatives, and all that stuff. So let's start it out the same way. We have 3x to the third plus 8x squared plus 6x plus 4, and we are dividing by x plus 2. People don't usually write this in parentheses, but inherently that's in parentheses. People typically don't write them. But. So we're going to do the same thing. The first thing we did was we looked at this 38 and this 12. It turns out that with polynomials, because it's okay for us to overshoot, all we really have to look at are the first terms of each polynomial. And we ask ourselves, what would you multiply x by to get 3x to the third? Well, you'd need a factor of 3, right? And then you'd need how many more factors of 2? I just said it. How many more factors of x? 2, right? So if you multiply x by 3x squared, the result would be 3x to the third. So we're going to put 3x squared right here. And I place this so that I'm lining up my place values, but in reality it doesn't really matter where they are because you have that x squared there to tell you what place value it is. So it doesn't really matter where you put it. I'm kind of neurotic about lining them up. So next, what should we do? So what did we do next here? We put this 3 right here. And then what was the next thing that we did? The 8? No, so don't look over here. Look over there. What's the next thing we did after we wrote that 3? No.
Put zeros.
Multiply it so you can get rid of the 3x.
Yeah, we multiplied 3 times 12 next, right? That's how we got this 36. So that we could subtract. So same thing here. I'm going to multiply 3x squared by x plus 2. So there's distributing involved here. I have to multiply by the entire thing. So 3x squared times x is 3x to the third. And 3x squared times 2 is 6x squared. What we just did there was 3x squared times x plus 2. I'll let you stare at it for a minute. So when we did this division, the first thing we did was say that 12 goes into 38 3 times. And then we said 3 times 12 is 36. So we said that multiplying x by 3x squared gets me 3x to the third, which is really us saying that x goes into 3x to the third 2x squared times. That just sounds weird when you use those words, like, which is why we restated a little bit. And then we multiplied what we put up top by our divisor. Just like we multiplied the 3 by the 12 to get 36, we multiplied 3x squared by x plus 2 to get 3x to the third plus 6x squared. So we're doing the same process. It looks very different. Now we're going to subtract, just like we did over here. We said this gives me 264 when I subtract. So the key with polynomials is that you need parentheses. So we're subtracting this whole entire thing. I can't draw a straight line. Anyway, 3x to the third minus 3x to the third is 0. That always happens. So that whatever it is that you're putting up top is going to get rid of the first term when you subtract. If it doesn't, then you pick the wrong thing up top. And then 8x squared minus 6x squared. So those parentheses say that negative applies to everything. So I'm doing 8x squared minus 6x squared, which gives me 2x squared. You can put a plus right here if you want. And then 6x minus 0 is 6x, and 4 minus 0 is 4. Yeah? So now we're going to repeat that same process. So there were like 3 steps there. We figured out what to put on top. We multiplied that by our divisor, and then we subtracted. We're just going to repeat those 3 steps over and over again until we're done. So now I want to know, what do I multiply this by to get this? Mm-hmm. Now we're going to multiply 2x by x plus 2. So 2x times x is 2x squared. And 2x times 2 is 4x. In parentheses, subtract. So 2x squared minus 2x squared is 0. Again, that always has to happen in that first term. And then 6x minus 4x is 2x, and 4 minus 0 is 4. And then we're going to repeat the process again. Are you guys seeing like how it's the same problem?
Yeah.
Yes.
How do you get the 4x again?
So I did 2x times x, and then 2x times 2. So I'm distributing that 2x to both terms in my divisor. So we did 2x times x plus 2. What? It's so cool, right?
Yeah,
I mean, it's
that's freaking
cool. Okay, so now what do I have to, we're going to do the same thing again. So what do I have to multiply x by to get 2x? Just 2, right?
Yeah.
So plus 2. And then we're going to multiply 2 by x plus 2. So distributing 2 times x plus 2 is 2x plus 4, parentheses, subtract, and we get 0. No, it's very right. This is the key to all of mathematics, is that this is nothing new, right? Like, we get to algebra and we're like, oh, all of a sudden you're putting x's and everything's different. it's not different. It's just an extension of what we already know how to do with whole numbers. So these are exactly the same problem, and you can, if you look at the coefficients, you can see like every single coefficient matches up with the place values over here. So it's literally the same problem. We just have incorporated these powers of x instead of having a 100s place and a 10s place and a 1s place, and so on and so forth, which in a lot of ways makes it nicer. Now we have to do one that involves some negative numbers, because this is where people make mistakes, is with the signs, is where it gets a little tricky. But the process itself, you're just repeating those same 3 steps. What goes on top, multiply, and then subtract, and then repeat the process again. So let's do another one before we go. That one's good. So let's do 12x to the third plus 42x squared minus 10x minus 41 divided by 2x plus 7. So again, we're going to just write this as long division. So 2x to the third plus 42x squared minus 10x minus 41, and then divided by 2x plus 7. So we are starting out with the 2x and the 12x to the third. So what do you have to multiply 2x by to get 12x to the third? So you need a factor of 6, and then how many factors of x? 2, so 6x squared. So now we'll multiply 6x squared by 2x plus 7. So 6x squared times 2x gives me 12x to the third. And then 6x squared times 7 gives me 42x squared. Oh, this was a bad problem for me to do, but that's okay. Parentheses and subtract. And then negative 10x minus 0, negative 41 minus 0. So this was pretty handy because that first term got rid of my first 2 terms, which means less work to do. So, but the process remains the same. We just move on to the next non-zero term, and we say, what do I need to multiply 2x by to get negative 10x? Now think about your signs. So it's going to be a negative 5, right? So minus 5. And so we're multiplying a negative 5 by 2x plus 7. So negative 5 times 2x is negative 10x. Negative 5 times 7 is negative 14. Parentheses and subtract.
Wait,
Oh, it's 35. Holy camole. Sorry. So negative 10x minus negative 10x is 0. And then remember, so this is where you just want to go really slow. So you have negative 41 minus negative 35. So that's, so we're adding 35, which gives us 6. Negative 6, in fact. So I ended up with a remainder. As soon as the degree, when you subtract, is less than the degree of what you're dividing by, right? The degree of that term is 0, and the degree of that polynomial is 1. So if the degree down here is less than the degree up there, you can't divide into it, right? Like that would be like saying how many times does 27 go into 6, which doesn't make sense, right? We can do it as a fraction, but we can't do it as a whole number. And so we have to think about what to do with the remainder. Oh my gosh, it is past time to go. I could go on like this forever. Let's pick up on this on Monday. So when you guys get to the division problems on your homework, you can just stop. Like, you don't have to do any of the division. We will pick up. I mean, if you want to try a few, that's cool. But we'll definitely pick up and talk. I don't want to rush through this because it's important and you kind of have to take it slow. So we'll just pick up on Monday.